Right now, more than 1 million miles from Earth, the James Webb Space Telescope is staring into a part of the universe where something does not seem to fit. Tiny red points are scattered across the oldest reaches of space, glowing at a time when objects like them should have barely begun to exist. At first, they looked almost meaningless, small crimson dots buried behind distant galaxies. But the deeper scientists looked, the stranger they became. They were too bright, too compact, and far too early. Now, astronomers may finally know what is hiding inside them. Soon, you will meet a black hole hiding behind a perfect mask, gas spinning at 600 meters a second. And the answer does not simply solve the mystery, it creates a much bigger problem. If you like the video, don't forget to leave a like and subscribe. It makes a huge difference, and I appreciate every single one of you. Now, let's begin. The first images from the James Webb Space Telescope were supposed to be a celebration. After decades of planning, years of construction, and one of the most difficult space missions ever attempted, Webb had finally unfolded its giant golden mirror nearly 1 million miles from Earth. Astronomers expected distant galaxies, ancient stars, and perhaps a few surprises. They were right. They just did not expect the surprise to be so small. Hidden among the brilliant galaxies were tiny points of deep red light. At first, they looked almost meaningless, faint crimson specks buried in the background of the universe. But they kept appearing. One image after another, one region of the sky after another, the same compact red object showed up again and again. That repetition caught the attention of scientists because the universe rarely repeats itself so neatly. Every patch of sky is different, yet these mysterious dots seem to belong to an entire hidden population. The first question was whether they were even real. Astronomers know that remarkable discoveries can begin with very ordinary mistakes. A flaw in a detector can create false signals. Cosmic rays can leave bright marks on a camera. Heat, dust, electronic noise, or errors in image processing can all imitate distant objects. So the research teams checked the data carefully. They compared separate observations, examined different instruments, and returned to the same regions of sky at different times. If the dots were defects, they should have vanished or shifted. They did neither. The red dots remained exactly where they were. They were not marks inside the telescope. They were real objects scattered across the distant universe and sending genuine light toward Webb's mirror. Then the mystery became even stranger. Many of these objects were completely absent from images taken by the Hubble Space Telescope. Hubble had spent more than 30 years observing some of the same regions, creating the deepest and most famous views of the cosmos ever captured. Astronomers knew those fields in extraordinary detail, yet when they compared the old images with Webb's new observations, the red dots were missing. It was as though an entire population of cosmic objects had been standing behind an invisible curtain, waiting for a telescope with the right kind of vision to pull it aside. That difference mattered because Hubble was not a weak or outdated instrument. It had transformed astronomy, revealed galaxies billions of light-years away, and helped measure the expansion of the universe. If Hubble had failed to see these objects, then the objects had to be unusual in a very specific way. Their light was either too faint, too stretched, or hidden in a part of the spectrum Hubble could not fully reach. As Webb searched farther into the ancient universe, more of the dots appeared. They were incredibly compact, often looking almost like single stars despite sitting at enormous distances. A normal galaxy spreads its glow across a wide region filled with billions of stars, like a city shining across a dark landscape. These objects did not. Their light seemed compressed into tiny points, as though an entire city had been squeezed into the glow of a single window. That alone made them strange, but their distance made them far more important. In astronomy, distance is also time. Light from the moon takes a little over 1 second to reach Earth. Light from the sun takes about 8 minutes. Light from the nearest star beyond our solar system travels for more than 4 years before reaching us. The light from these red dots had been travelling for billions of years. When Webb observed them, it was not seeing them as they are now. It was seeing them as they existed when the universe itself was still young, long before the Sun, Earth, or the familiar Milky Way had formed. These were not merely distant objects, they were photographs from the universe's childhood, and that was where the real problem began. According to the standard picture of cosmic history, the early universe should have been a rough construction site. The first stars were only beginning to ignite. The earliest galaxies were expected to be small, unstable collections of gas and newborn stars, slowly assembling through collisions and mergers. The foundations of the cosmic city were still being laid, yet the red dots appeared bright, compact, and surprisingly developed. Finding them was like arriving at a building site that should contain only scaffolding and discovering a completed skyscraper rising above the dust. At first, astronomers tried the safest explanation. Perhaps these were simply distant galaxies whose light had been stretched by the expansion of the universe. That idea made sense because extremely distant galaxies often appear red. As light crosses expanding space, its waves are pulled longer, shifting toward red and eventually into infrared. Webb was built to see exactly that kind of stretched light. But the more data scientists collected, the harder the simple galaxy explanation became to defend. The dots were too bright for their apparent size, they were too compact. Some seemed to contain far more energy than such small young galaxies should have been able to produce. And instead of finding only a few unusual examples, Webb kept discovering them across multiple surveys. They were not isolated accidents, they were a population. Scientists eventually gave them a name, not because they understood them, but because they needed a way to discuss them. The name was almost strangely ordinary, Little Red Dots. No dramatic title, no complicated phrase, just a description of what appeared in the images. Behind that simple name, however, was a serious question. What could create so much light inside such a small region, so early in the history of the universe? The answer mattered far beyond the objects themselves. If the dots were ordinary galaxies, then the young universe had built stars and structures much faster than current models allowed. If they were something else, then an entire class of powerful objects had remained hidden from astronomers for decades. Either possibility meant that the first chapters of cosmic history were incomplete. That is what made the discovery so unsettling. James Webb had not simply found a few strange points of light. It had uncovered evidence that the early universe may have developed faster, more violently, and through different processes than scientists expected. Every great telescope has changed humanity's view of the cosmos. Galileo showed that Earth was not the centre of everything. Hubble revealed that the Milky Way was only one galaxy among billions. Now Webb was looking deeper than either of them, and finding a universe that did not perfectly match the story written in our models. Before scientists could understand what the red dots were, they first had to solve a simpler mystery. How could an entire population of bright cosmic objects remain invisible for so long, only to appear almost immediately when Webb opened its golden eye? The answer did not begin with the red dots themselves. It began with the telescope that found them. At first glance, James Webb and Hubble seem like two versions of the same idea. Both orbit beyond Earth's atmosphere. Both use giant mirrors to collect faint light from the universe. Both have transformed astronomy by revealing places no human had ever seen before. But in reality, they were built to answer different questions, and that difference turned out to be the key to one of the biggest discoveries in modern astronomy. Imagine standing on a beach at sunset. As darkness falls, your eyes slowly lose sight of the landscape around you. The colours fade, details disappear, and eventually the world becomes little more than silhouettes. Now imagine putting on a pair of night vision goggles. The beach has not changed, but suddenly the invisible becomes visible. Warm rocks, distant trees, and people walking along the shore emerge from the darkness. That is essentially what happened when James Webb looked at the universe. For most of its remarkable career, the Hubble Space Telescope observed primarily visible light, the same narrow range of colours that human eyes can detect. It could see a little beyond that range into infrared light, but only a short distance. James Webb was designed very differently. Almost everything about it, from its enormous golden mirror to its sun shield the size of a tennis court, was built for one purpose: seeing the universe in infrared. Infrared is often described as heat, but that is only part of the story. Every warm object gives off infrared radiation, from a glowing fireplace to your own hands. More importantly for astronomy, infrared light can reveal objects that visible light cannot. It passes through clouds of dust, uncovers regions where stars are being born, and most importantly, captures light that has been stretched across billions of years of cosmic expansion. That stretching is one of the strangest consequences of living in an expanding universe. When people hear that galaxies are moving away from one another, it is easy to imagine them racing through empty space like cars driving down a highway. But that picture is misleading. A better way to imagine it is to think of raisins inside a loaf of bread as it bakes. The raisins are not moving through the dough. Instead, the dough itself expands, carrying every raisin farther from the others. The universe behaves in much the same way. Space itself is expanding, and as light travels through that expanding space, something remarkable happens. The light waves are stretched along with it. Each wave becomes slightly longer than it was before. As the journey continues over billions of years, those tiny changes accumulate until the light shifts completely out of the visible spectrum and into infrared. Astronomers call this effect redshift, because the light moves toward the red end of the spectrum before disappearing into wavelengths invisible to our eyes. The farther away an object is, the longer its light has travelled. The longer it has travelled, the more the universe has stretched it. By the time the light from the little red dots finally reached our corner of the cosmos, much of it no longer looked anything like the light that originally left those distant objects. It had been transformed into exactly the kind of infrared glow James Webb was built to detect. That explains why Hubble missed them. It was never looking in the wrong direction. It had spent decades observing many of the same regions of space. The light from the red dots was reaching Hubble's mirror the entire time. But by the end of its journey, that light had shifted beyond most of the wavelengths Hubble could effectively observe. It was like trying to hear the deepest notes of a piano while wearing earplugs that block low frequencies. The music is there, but the instrument cannot fully detect it. Webb removed those earplugs. Its mirror is another crucial part of the story. At 6.5 meters across, Webb's primary mirror has more than 6 times the light collecting area of Hubble's. That difference is not simply about producing prettier pictures. A larger mirror gathers more photons, the tiny packets of light arriving from unimaginably distant objects. When those photons have been travelling across the universe for over 13 billion years, every single one becomes precious. Imagine trying to fill a bucket during a light drizzle. A small bucket collects water slowly, while a much larger one gathers enough to notice the rainfall much sooner. Webb's mirror acts like that larger bucket, collecting enough ancient light to reveal objects that had previously remained hidden in the background. The combination of infrared vision and greater sensitivity changed everything. Almost overnight, the early universe became far more crowded than astronomers had expected. Instead of finding only a handful of distant galaxies, Webb uncovered thousands of compact red sources scattered throughout cosmic history. It was as though explorers had entered what they believed was an empty valley, only to discover an entire city concealed beneath the morning fog. Yet seeing the object solved only one mystery while creating another. If these red dots had simply been ordinary galaxies hidden by redshift, their properties should still have matched existing theories. But as researchers began measuring their brightness, estimating their sizes and analysing their light, the numbers refused to cooperate. The dots appeared extraordinarily compact. They radiated immense amounts of energy from regions that seemed impossibly small. In many cases, they looked less like galaxies and more like single brilliant points, despite existing billions of light years away. That combination should not have been possible. A young galaxy can certainly shine brightly, but it usually spreads that light across billions of stars occupying an enormous volume of space. These objects seem to concentrate an astonishing amount of light into areas far smaller than expected. It was like seeing the glow of an entire metropolis coming from a single apartment window. The more astronomers examined them, the more uncomfortable the data became. If the observations were correct, and every new survey suggested they were, then the little red dots were not simply another class of distant galaxies waiting to be catalogued. They represented something fundamentally different, something that did not fit comfortably into existing models of the young universe. The telescope had done its job perfectly. It had opened a new window onto the cosmos. Now scientists had to figure out what, exactly, they were looking through. Because hidden inside the faint infrared glow of those tiny crimson dots was a source of energy so intense that it challenged nearly every expectation about how the first structures in the universe should have formed. Astronomers could now explain why Webb saw the little red dots, but visibility was only the beginning. A telescope can reveal that something exists without revealing what it is. To answer that question, scientists had to do what astronomers have always done with objects too distant to touch. They had to read the light. Light is not only an image, it is a record. When light is spread apart into its individual wavelengths, it forms a spectrum, a long band of colour filled with subtle lines, bends and gaps. To the eye, it may look like a distorted rainbow. To an astronomer, it is closer to a barcode printed by the object itself. Different atoms leave different marks. Hydrogen writes one pattern, oxygen another. The shape of the spectrum can reveal temperature, motion, chemical composition, and the type of engine producing the energy. For the little red dots, that spectrum was the closest thing scientists had to opening a sealed box. The first interpretation seemed straightforward. Perhaps the dots were extremely young galaxies, packed with enormous numbers of stars. Their red appearance could be explained by distance, and their brightness might come from intense bursts of star formation. The early universe was full of gas, and gas is the raw material from which stars are built. It was reasonable to imagine small galaxies igniting with newborn suns, shining furiously during a brief stage of rapid growth. For a time, that explanation appeared to work. Then researchers began estimating how many stars would be required. A galaxy shines because its stars add their light together. If a distant galaxy appears bright, astronomers can calculate roughly how much stellar mass must be producing that glow. The process is not perfect, especially for objects this far away, but it provides an important test. If the red dots were ordinary stellar systems, their brightness and size should form a physically believable picture. Instead, the picture became almost impossible. The dots were not only bright, they were extremely compact. Webb could not resolve many of them into broad structures, spiral arms, or extended clouds of stars. Their light appeared concentrated into regions far smaller than expected. In some cases, the source seemed to occupy only a tiny fraction of the space, taken up by a normal galaxy of similar brightness. Imagine looking across an ocean at night and seeing the glow of an entire coastal city. You would expect that light to stretch for miles along the horizon. Now imagine the same amount of light coming from a single lighthouse. The brightness might be real, but its concentration would immediately tell you that something unusual was happening inside. That was the problem with the red dots. To explain them entirely with stars, scientists had to place an enormous stellar population inside an incredibly small region. The density would have been unlike anything seen in mature galaxies nearby. Stars that normally drift across vast distances would need to be packed together almost wall to wall on an astronomical scale. Our own part of the Milky Way is mostly emptiness. The Sun may feel surrounded by stars when viewed from Earth, but the nearest one is more than 4 light-years away. If the Sun were a grain of sand, the next star would be another grain separated by many kilometers. Galaxies contain billions of stars, yet most of their volume is open space. The red dots seem to demand something very different. To produce their apparent brightness with stars alone, some models required stellar systems so tightly compressed that thousands of suns might occupy a region where far fewer would normally fit. The gravitational environment would be extreme. Close encounters would become common. Stars could disrupt one another, collide, or be thrown from the system entirely. The neat picture of a compact young galaxy began to resemble a crowded room whose walls should have collapsed under the pressure. There was another problem. A young galaxy with such intense star formation should not hide its structure completely. New stars are born inside clouds of gas and dust, often forming irregular knots and bright clusters. Early galaxies are expected to be messy because they are assembled through streams of gas and collisions with smaller systems. Their light should spread across uneven regions like sparks flying from a fire. Many of the dots did not look that way. They remained sharply concentrated, almost point-like, as though a single central source was overpowering everything around it. That clue began to shift the investigation. Astronomers asked whether the glow might be coming from something other than stars. There are very few objects capable of producing the energy of a galaxy from a region so small. One of them is a feeding black hole. A black hole itself gives off no light. Once matter crosses its boundary, no signal can return. But the material falling toward it can become one of the brightest things in the universe. Gas does not drop straight down like a stone into a well. It circles, accelerates, and flattens into a rapidly spinning disk. As neighbouring layers move at different speeds, the gas heats to extraordinary temperatures and releases enormous amounts of radiation. A single active black hole can outshine billions of stars. This possibility explained the compactness. Instead of requiring an impossible city of stars squeezed into a tiny volume, the brightness could come from one central engine. The light would appear concentrated because the energy was being produced near the black hole, inside a region small enough to fit within a planetary system. But suggesting a black hole was not the same as proving one. Astronomers needed a clearer signature, something written into the spectrum that stars alone would struggle to produce. They found it in the shape of certain emission lines. When atoms in hot gas release light, they create narrow features at precise wavelengths. Under calm conditions, those lines remain relatively thin. But when the gas is moving at extreme speed, the lines spread out. Some material rushes toward Earth, shifting its light slightly toward shorter wavelengths. Other material moves away, stretching its light in the opposite direction. The combined signal becomes broad, like a musical note smeared across many pitches. Several little red dots showed exactly this kind of broadening. The gas was not drifting gently through a young galaxy. It was racing at thousands of kilometers per second. At those speeds, the material could cross an entire continent in only a few seconds. Ordinary stars could stir gas through winds, explosions, and gravitational interactions. But producing such sustained motion inside such a compact region required an enormous central mass. The gas appeared to be orbiting something with a gravitational pull far stronger than any cluster of ordinary stars could easily provide. The black hole explanation was no longer simply convenient. It was becoming difficult to avoid. The broad spectral lines resembled those seen around active galactic nuclei, the brilliant centers of galaxies powered by feeding supermassive black holes. In the modern universe, these objects are well known. Some blaze as quasars, visible across billions of light years. Their light comes from gas heated as it spirals toward black holes, millions or billions of times more massive than the Sun. The little red dots seem to contain smaller versions of the same machinery, but operating at a time when the universe was still remarkably young. That raised a disturbing possibility. If the dots were powered by black holes, then those black holes were already enormous. The brightness of the sources and the speed of the surrounding gas suggested masses ranging from hundreds of thousands to millions of suns. These were not the fresh remains of recently collapsed stars. They were giants, already feeding and already dominating their surroundings. The discovery replaced one impossible explanation with another. The stars no longer needed to be packed into densities that threatened to break the models. Instead, scientists had to explain how massive black holes appeared so early in cosmic history. It was like discovering that the strange light inside a distant house didn't come from thousands of candles, but from a furnace powerful enough to illuminate an entire city. The mystery had changed shape, but it had not become smaller. There was still one major contradiction. Feeding black holes are usually loud across the electromagnetic spectrum. They produce intense X-rays, ultraviolet radiation, and sometimes powerful radio jets. These signals are among the most reliable tools astronomers use to find active black holes. Yet the little red dots were strangely quiet. They carried the spectral motion of gas trapped by monstrous gravity. Their compact brightness pointed toward a central engine. But when astronomers searched for the high-energy signals that should have confirmed the answer, many of the dots seemed almost silent. Something powerful was shining inside them, and something else was hiding the evidence. The evidence was beginning to point toward black holes, but one problem refused to disappear. If the little red dots were really powered by feeding supermassive black holes, astronomers should have recognized them almost immediately. Black holes may trap light beyond their event horizons, but the regions around them can become some of the brightest places in the universe. Gas falling inward forms a rapidly spinning disk, and as its layers grind past one another, they heat to extraordinary temperatures. That heated material releases visible light, ultraviolet radiation, and powerful X-rays, creating a signal so intense that astronomers can often detect an active black hole from billions of light years away. For decades, X-rays have been one of the clearest fingerprints of a feeding black hole. Find the X-rays, and there is usually a powerful gravitational engine nearby. That is why the little red dots were so confusing. Their compact brightness and rapidly moving gas pointed toward massive black holes. Yet when scientists searched for the expected high-energy radiation, most of the dots appeared strangely quiet. Some produced only weak traces of X-rays, while many seemed to produce none at all. It was like finding a factory whose windows glowed through the night while every machine inside remained silent. The energy was clearly there, but one of its loudest signals was missing. For a time, researchers wondered whether the black hole interpretation had been wrong. Perhaps an unfamiliar population of stars was producing the glow. Perhaps the broad spectral features had another explanation. But the alternatives struggled to account for all the evidence at once. The light remained too concentrated, the gas was moving too quickly, and the total energy was too great to be explained comfortably by stars alone. Instead of abandoning the black hole idea, astronomers began asking whether the X-rays were truly absent or merely hidden. That possibility shifted the entire investigation. Imagine placing a powerful lamp inside a room with thick stone walls. The lamp may be blazing, but almost none of its direct light reaches the outside. The source has not become weaker. Its surroundings have simply trapped the evidence. The early universe provided the perfect material for such a hiding place. Hydrogen, the simplest and most abundant element in the cosmos, filled the young universe in enormous quantities. Around some growing black holes, this gas may have gathered into thick, dense cocoons. These were not delicate clouds drifting through space. They were massive layers of material packed tightly around the central engine, dense enough to absorb much of the radiation trying to escape. Inside the cocoon, the black hole continued to feed. Gas spiraled inward, accelerated and heated until it produced a flood of high-energy light. But instead of travelling freely into space, much of that radiation collided with the surrounding hydrogen. The X-rays transferred their energy into the gas, warming the cocoon from the inside like a furnace buried beneath a mountain. The trapped energy did not vanish. It changed form. Once heated, the surrounding gas began to release that energy at longer wavelengths, especially in infrared light. Webb was not necessarily seeing the violent black hole directly. It was seeing the warm outer shell that surrounded it. The cocoon absorbed the scream from the centre and returned it to the universe as a softer infrared glow. This explained why the little red dots could shine so brightly in Webb's instruments, while remaining weak in X-rays. The central source was still producing immense amounts of energy, but the thick gas around it was acting like a heavy curtain. High-energy radiation remained trapped behind the fabric, while heat slowly leaked through. The same idea also explained their compact appearance. Although the cocoon could extend across a significant region, the energy originated near a single central source. From billions of light-years away, the whole structure blurred into one small point. The object looked simple from the outside, even though the interior contained gas moving at extreme speed around a growing black hole. The calm appearance was therefore deceptive. Each neat red point could hide a storm of falling matter, violent heating, and intense radiation. Webb was seeing the glow of the walls, not the fire raging behind them. That hidden stage may also explain why astronomers had overlooked these systems for so long. Traditional searches for active black holes often rely on X-rays, radio waves, or bright ultraviolet light. If the cocoons blocked those signals, the objects would slip past many of the methods designed to find them. They were not truly invisible. They were simply wearing a disguise that most telescopes were not built to see through. James Webb changed that because infrared light is especially good at revealing heat buried behind gas and dust. Its instruments could detect the energy that had been absorbed and reprocessed inside the cocoon. Where other telescopes saw silence, Webb saw the warm outline of the hidden source. The explanation was elegant, but it created a new question. A black hole feeding this violently should not remain buried forever. As it consumes gas, it gradually eats through the material around it. At the same time, radiation and powerful outflows push against the cocoon from within. The black hole is both feeding on its cover and tearing it apart. Over time, the cocoon should begin to thin. Small openings may appear, allowing some of the trapped radiation to escape. At first, only narrow beams of X-rays might leak through. Later, as more gas is consumed or blown away, the hidden engine would become increasingly exposed. The soft infrared dot would begin to change into the bright, unmistakable form of an active galactic nucleus. This meant the little red dots might not be permanent objects. They could represent a temporary phase in the life of an early supermassive black hole, a period when the central engine was already powerful but still buried inside the material that helped it grow. The dots would be less like a separate species and more like a stage of development, similar to a structure hidden behind scaffolding before the final building is revealed. That idea carried an important prediction. Somewhere among the thousands of little red dots, astronomers should find an object caught midway through the transformation. Its cocoon would still be mostly intact, so it would remain bright in infrared, but cracks in the surrounding gas would allow some X-rays to escape. Such an object would link the silent red dots to the exposed black holes seen later in cosmic history. Researchers began searching for exactly that kind of transition. Most of the dots remained quiet, their cocoons apparently thick enough to conceal the engines inside. Then one object broke the pattern. It produced a real X-ray signal, faint compared with a fully exposed quasar, but strong enough to suggest that the buried source was beginning to emerge. That single detection became a crucial piece of evidence. It suggested that the missing X-rays had not been missing at all. They had been trapped, and now part of the radiation was finally escaping through a weakening shell. The object appeared to be caught between two stages, still wearing the red disguise but beginning to shed it. For astronomers, it was like finding one frame from the middle of a transformation. On one side were the silent infrared dots, buried deep inside thick gas. On the other were the familiar active black holes that shine openly across the universe. This object stood between them, showing how one form might become the other. The cocoon explanation solved the mystery of the missing X-rays, but it also revealed something more unsettling. These black holes were not merely present in the young universe. They were actively feeding, rapidly growing, and already powerful enough to reshape their surroundings. And once scientists began estimating how massive they had become, the timeline of the early universe started to break. The deeper astronomers looked into the little red dots, the more serious the problem became. The hidden black holes were not merely active. Many of them appeared to be enormous, with masses reaching hundreds of thousands or even millions of times that of the Sun. In the modern universe, black holes of that size are not unusual. They sit at the centres of large galaxies, where they have had billions of years to feed, merge, and grow. The shock was not their size alone. It was the age of the universe when they were already that large. James Webb was seeing some of these objects when the cosmos was only a few 100 million years old. On the scale of cosmic history, that is almost the beginning. If the universe were compressed into a single year, these black holes would appear in the first weeks of January, already massive and already feeding. It was like discovering an ancient mountain range in a landscape that should still have been soft mud. According to the traditional picture, giant black holes begin with much smaller seeds. A massive star reaches the end of its life, collapses under its own gravity, and leaves behind a black hole perhaps several times heavier than the Sun. That small remnant can then begin to grow. It swallows gas, tears apart stars, and sometimes merges with other black holes. Over long stretches of time, the seed gains mass until it becomes the supermassive object found at the centre of a mature galaxy. The process sounds simple, but it has a speed limit. A black hole cannot consume unlimited amounts of matter without consequences. As gas falls inward, it heats and releases radiation. That radiation pushes outward against the gas still trying to fall in. The harder the black hole feeds, the brighter the surrounding disk becomes, and the more strongly that light resists the incoming material. Eventually, the outward pressure begins to balance the pull of gravity. It is similar to trying to pour water into a container while a powerful fan blows upward from inside it. At a low flow, the water falls in easily. Increase the flow too much, and the force coming back begins to scatter the water away. A feeding black hole faces the same kind of struggle. Its own brilliance can push its fuel out of reach. This creates a natural ceiling on how quickly a black hole can grow under ordinary conditions. Even at that maximum pace, starting with a small stellar black hole and reaching millions of solar masses requires time. The problem is that the early universe did not provide enough of it. Some of the little red dots seem to contain black holes that should have needed far longer to grow than the universe had existed when Webb observed them. The arithmetic became uncomfortable. A small seed could double its mass again and again, but each doubling took time, and the cosmic clock was already running. To reach millions of suns within a few 100 million years, the black hole would need to feed nearly without interruption, always close to the maximum rate, with no long pauses and no shortage of gas. Even then, some objects remained difficult to explain. That left astronomers with two broad possibilities. Either the black holes grew faster than the standard limit allows, or they did not begin small. The first idea is that the young universe may have forced gas into black holes at extraordinary rates. In the early cosmos, matter was packed more densely than it is today. Galaxies were smaller, gas clouds were thicker, and streams of hydrogen flowed into developing systems from many directions. Under those conditions, a black hole might briefly consume matter faster than the usual limit, especially if a dense cocoon trapped much of the radiation that would otherwise push the gas away. The same blanket that hid the X-rays could also have helped the black hole grow. If radiation remained trapped inside the surrounding material, it would have less power to blow incoming gas back into space. The black hole could continue feeding while buried inside its own fuel supply, like a fire burning inside a sealed furnace where the heat remains concentrated instead of escaping. Astronomers call this kind of extreme growth super-Eddington accretion. Though the name is less important than the idea, it means the black hole temporarily eats faster than the normal balance between gravity and radiation would suggest. Computer models show that short bursts of this behavior may be possible. The difficulty is sustaining it long enough to build the largest black holes Webb appears to be seeing. The other possibility is even more dramatic. Perhaps some of these black holes skip the small seed stage completely. Instead of beginning as the collapsed core of a star, a black hole could form from the direct collapse of an enormous cloud of gas. The early universe contained vast reservoirs of hydrogen, and in rare places, gravity may have pulled that material together faster than it could break apart into stars. If the cloud remained hot and smooth, avoiding fragmentation, the entire structure might collapse inward as one enormous mass. The result would not be a black hole weighing 10 or 20 suns. It could be born with tens of thousands, perhaps even hundreds of thousands of solar masses. Such a black hole would begin its life halfway up the mountain rather than at the bottom. The difference is like building a castle stone by stone compared with lowering an entire tower into place. The first method is slow, requiring countless small additions. The second begins with a structure already towering above the ground. A heavy seed would still need to grow, but it would need far fewer doublings to reach the masses suggested by the little red dots. This idea, known as direct collapse, has existed for years because astronomers needed some way to explain the earliest known quasars. Webb has now made the problem far more widespread. Instead of finding only a few exceptional giants, it has revealed a large population of compact objects that may contain overgrown black holes in the young universe. If even a fraction of them form through direct collapse, then the process may have been more important than scientists once believed. Yet direct collapse is not an easy solution. A gas cloud normally cools as it contracts. Cooling allows it to break into smaller clumps, and those clumps become stars. To collapse as one enormous object, the cloud must somehow remain hot enough to resist fragmentation. Nearby radiation, unusual chemical conditions, or violent streams of incoming gas might help, but the exact recipe remains uncertain. No telescope has ever watched a direct collapse black hole form from beginning to end. The process is supported by theory and simulation, but not yet by a clear observation. The little red dots may be evidence that it happened, but they are not a photograph of the birth itself. They show the possible outcome, not the moment of creation. There is another clue hidden in the relationship between these black holes and their galaxies. In the nearby universe, the mass of a central black hole tends to follow the size of the galaxy around it. Large galaxies usually contain large black holes, while smaller galaxies host smaller ones. The two appear to grow together over time, like a building and its foundation rising in proportion. The little red dots seem to break that pattern. In many cases, the black hole appears far too massive for the amount of starlight surrounding it. The engine is enormous, but the visible galaxy is faint and underdeveloped. It is like finding a ship's engine inside a wooden rowboat, powerful enough for an ocean liner but surrounded by a vessel that has barely been built. This mismatch suggests that the black hole may have grown before the galaxy around it. Instead of forming inside a mature stellar system, it may have arrived early and influenced how the galaxy developed. Gas falling into the black hole would not only feed it, the energy released by that feeding could heat nearby clouds, drive powerful winds, and either encourage or suppress the formation of stars. A young black hole could therefore act as both architect and demolition crew. Its gravity might pull material inward, helping build the central region of a galaxy, while its radiation blasts other material away. The final structure would emerge from a struggle between attraction and destruction, with the black hole shaping its surroundings from the beginning. That possibility reverses the familiar story. Astronomers once imagined galaxies forming first, with black holes growing slowly at their centres. The little red dots suggest that in some cases, the black hole may have taken the lead. The monster could have arrived before the city, and the city may have been forced to grow around it. This is why the answer to the red dot mystery is not entirely comforting. Discovering hidden black holes explains the compact glow, the broad spectral lines, and the missing X-rays. But it also reveals that massive cosmic structures appeared earlier than expected. The old timeline no longer fits neatly, and every proposed solution demands conditions more extreme than the standard picture allowed. Either the first black holes were born far larger than imagined, or they grew at rates that pushed against familiar physical limits. Perhaps both occurred in different systems. Whatever the answer, the early universe was not a quiet nursery where small objects slowly matured. It was a violent workshop capable of building giants with astonishing speed. And these giants may not have simply lived inside the first galaxies, they may have helped create them. By now, the little red dots had gone from being faint curiosities in Webb's first images to some of the most important objects in modern astronomy. Scientists had uncovered a convincing explanation for much of what they were seeing. The compact light, the hidden X-rays, the broad spectral lines, and the immense energy could all be explained if these objects were rapidly growing supermassive black holes buried inside thick cocoons of hydrogen gas. It was an elegant picture, one that connected many of the clues into a single story. But in science, solving one mystery often reveals another. If these black holes really were the ancestors of the giant black holes found at the centres of galaxies today, then astronomers should be able to watch that transformation unfold across cosmic time. The farther away Webb looks, the younger the universe appears. By comparing objects at different distances, researchers can build something like a family album, watching the same type of object at different stages of its life. That is exactly what they began to do. The youngest examples appear as the compact little red dots Webb first discovered. Their thick cocoons hide much of the violent activity taking place inside, allowing only infrared light to escape. Later in cosmic history, some of those cocoons seem to become thinner. Small amounts of high-energy radiation begin leaking through, revealing black holes that are slowly shedding their disguise. Eventually, the surrounding gas is either consumed by the black hole itself or blasted away by powerful outflows. The once hidden object transforms into a fully exposed active galactic nucleus, the kind astronomers have been studying for decades. In many ways, the process resembles watching a dense morning fog slowly lift. At first, you can only see a faint glow behind the mist. As the fog thins, outlines begin to emerge. Finally, the entire landscape comes into view. The object has not changed nearly as much as your ability to see it. The same may be true for these ancient black holes. James Webb may simply be observing a stage that older telescopes could never witness. If that interpretation is correct, then the little red dots are not strange exceptions to the history of the universe. They are a missing chapter. They represent a phase every giant black hole may have passed through billions of years ago before becoming the familiar monsters we observe today. That possibility carries enormous consequences because nearly every large galaxy in the modern universe contains a supermassive black hole at its centre. Our own Milky Way is no exception. Buried deep within its core is Sagittarius A star, a black hole containing more than 4 million times the mass of the Sun. Today it is relatively quiet, but it was almost certainly far more active in the distant past. It is entirely possible that our own galaxy once looked remarkably similar to the little red dots Webb now observes. Long before the Milky Way developed its graceful spiral arms, before the Sun was born, and before Earth even existed, its central black hole may have been wrapped inside a dense cocoon of gas, growing rapidly while hidden beneath layers of hydrogen. In a sense, Webb may be showing us what our own cosmic home looked like more than 13 billion years ago. Yet even this remarkable picture leaves several questions unanswered. One of the biggest mysteries is why the little red dots appear so frequently during one period of cosmic history, and then become increasingly rare. They seem to flourish when the universe is only a few 100 million years old, but later they almost disappear. The black holes themselves cannot simply vanish. Gravity does not allow that. Something must have changed. The most likely explanation is that the dots never truly disappeared. They evolved. As the surrounding cocoons were stripped away, the objects stopped looking like little red dots and started looking like ordinary active galaxies. In other words, astronomers may have mistaken a change in appearance for a disappearance. The hidden population did not die out. It simply outgrew the stage that made it recognizable. Even so, researchers cannot yet say whether every little red dot follows the same path. Some observations hint that the population is more diverse than first imagined. When scientists examined many of these objects in different wavelengths, they noticed an intriguing pattern. Some appeared remarkably smooth and compact, almost perfectly round regardless of how they were observed. Others looked far more chaotic, showing distorted structures that hinted at galaxy mergers or violent interactions. The difference could mean that not all little red dots share the same origin. Some may represent isolated black holes growing quietly inside dense clouds of gas. Others may be fueled by galaxies colliding with one another, driving enormous quantities of matter toward their centers. Still others might involve processes astronomers have not yet considered. At the immense distances involved, even James Webb is working near the limits of what current technology can resolve. That uncertainty is what makes the discovery so exciting. Science is often imagined as a collection of answers, but its greatest moments usually begin with better questions. Every generation builds instruments capable of seeing farther than the last. Almost every time that happens, nature reveals something unexpected. Galileo found moons orbiting Jupiter. Hubble showed that the Milky Way was only one galaxy among countless others. James Webb is now exposing a universe filled with objects that challenge some of our oldest ideas about how cosmic structures first emerged. The title of this story suggests that the answer is not good. It is not good if you hoped our existing models already explained the early universe. Those models have been remarkably successful for decades, but the little red dots reveal cracks that cannot simply be ignored. They suggest that black holes may have formed earlier, grown faster, or begun much larger than many theories predicted. They hint that galaxies and black holes may have evolved together in ways we're only beginning to understand. That is not a failure of science. It is exactly how science moves forward. Every major breakthrough begins with an observation that refuses to fit. The little red dots are forcing astronomers to revisit assumptions that once seemed secure, to build new simulations, develop new theories, and gather even better observations. Some current explanations will survive that process. Others will not. The universe has no obligation to match our expectations, and that may be the most fascinating part of all. These tiny points of red light travelled across more than 13 billion years of expanding space before reaching Webb's golden mirror. During that unimaginable journey, civilizations rose and fell on Earth before a single photon completed its path. When those photons finally arrived, they carried more than a beautiful image. They carried a message from the universe's earliest years, one that had remained unread for almost the entire history of humanity. We're only beginning to understand what that message says. The little red dots remind us that the universe still holds chapters we've never read, hidden not because they were too far away, but because we had never built the right eyes to see them. And if something as small as a faint red speck can reshape our understanding of cosmic history, it is worth asking what other surprises are still waiting in the darkness, just beyond the limits of what we can see today. If you like the video, don't forget to leave a like and subscribe. It makes a huge difference and helps the channel grow.